But some of you, okay, especially people who are as old as me, or as old as Wei-san know, logic programming had really, really booming years, yeah? When the 5th generation project was at its peak, yeah? And I remember I attended one conference. That conference attracted 2,500 participants. That's unbelievable now. Okay, so I think Picat is rejuvenating logic programming. Okay, it provides logic programming concepts, okay, in a more accessible way. Okay, so I'm not sure Picat will, bring logic programming back, but we have a good start. And this is Hakan's Picat page. Okay, Hakan has been involved in this project since the very beginning. He has written more than 1,000 programs in Picat. Okay, so on his page you can find, I think, more than 800 programs, okay, written by him. And in May last year, these two authors I didn't know, Sergey Dimchenko and his wife, wrote a paper on declaratively solving Google CodeGen problems with Picat. Actually, several people were inspired by this paper. Last year, 5 participants, only 5, by a small number, but for a younger language like this, it's an encouraging number. 5 participants from 4 different countries used Picat in Google CodeGen, but only 1 used Prolog. And last August, again, Sergey Dimchenko, this magazine featured an article on Picat. So there was an article on writing concise, declarative, and efficient programs. Okay. So being declarative is good, but it must be efficient as well. Yeah? And September, we published a paper on planning as table logic programming. Okay. Well, as you will see in the demo, this planner really, really surprised many people. Planning has been a target problem for logic programming since 1960s. The first logic programming language was called planning, and then Prolog. Prolog, is reader Robert Kloss's book. The book has 2 chapters devoted to planning. And later on, many languages were proposed for solving planning problems, including ASP and many action languages. Okay, none of those languages was satisfactory. Okay, it is okay to model problems, but no, not efficient to solve them. So I think several years from now, this paper will be considered an interesting paper because it proposed a language that is powerful for modeling and solving planning problems. November last year, we published the first book on Picat. Okay, so you can see a lot of examples for dynamic programming. Okay, dynamic programming examples, constraint satisfaction problems, and planning problems. And we launched the page. Okay, so inspired again by Dimchenko's article. Okay, we launched a page. So a collection of solutions for Google CodeGen problems. Yeah. Actually, some people have told me I'm going to use Picat for this year's Google CodeGen competition. And in January this year, we published a paper on Picat set compiler. So, set is really, really hot. It is used everywhere, yeah? And there are many proposals for encodings, but there are really, really few working compilers. So this is one of the working compilers, and it is also a really, really good platform for exploring other encoding algorithms and optimizations. So last month, actually just right before I came here, So I posted an article on learning programming in Picat by examples from Google Collegian. Okay, it shows Dimchenko's paper was on how to solve Google Collegian problems declaratively. This article shows how to solve general, Google Collegian problems. Okay, programs are concise and easy to read, easy to write. Well, I don't. Well, at least if I were to participate in this, okay, I would have much better chance to do better than if I were to use C++. Yeah. Okay. So I'm not sure, people will win by using Picat. At least you get some competitive edge. Okay. So all right, now let me show you a brief demo. Okay. So here, well, you can just download. It's pretty easy to use this system. Only one executable. That's it. Okay. No setting, nothing. Yeah. One executable. Just type the name, and then you'll get started. I use Sigwin. Yeah. So go to the directory. Okay. So I created a folder for this flops wizard. It's here, flops. Okay. There are several examples. Okay. Let me show this Euler problem. Yeah. Well, actually, yesterday, Marcos gave a great talk on his COPB system. Yeah. And he used it. He used this example as a benchmark. Yeah, as a benchmark. And well, the BDD. It took a BDD. How many hours? 7 hours. Yeah, to find the solution. Okay. So, what is the problem? Let me change the font. Okay. So maximize. How to change the font? How to change the font?
Control Shift and plus plus.
Control Shift and plus plus.
No.
Control.
Okay, maybe we know.
No, this is the Sigwin. This is Sigwin.
Is it Minty? Is it?
Option fonts.
Oh, option.
Options?
Fonts.
Fonts.
Text.
Text.
Fonts. Fonts. Yeah. Oh, good. Let me make it larger. As larger. Today it should be good. Yeah. Okay.
Apply.
Oh, well, very good. Very good. Okay. I think Weda-san will be happy. I'll be happy too. Okay, so let me show you the program. Okay, so it is P something. Okay, the problem is, okay, how many 18-digit numbers n are there such that no digit occurs more than 3 times? Okay? Okay, good. So this is the program. Okay, it uses tabling. So what do we do? Okay, we create a list of digits, yeah, from 0 to 9, and then we use a count. Okay, so this is in the beginning, no digit has been used, so it's 0, 0, 0, 0. Okay, so this list shows how many digits have been used. Yeah, so the number cannot exceed 3, right? Okay, so then we call this, and then we also see how many digits we need to choose. In the beginning, it's 8 digits we will need to choose. Yeah, okay. So it is a pretty simple program. I think I need to reset it. Okay, so it's, sorry. And text. Font. And make it 20 should be good?
18.
18?
Apply.
Oh, it's very good, yeah? So, well, this program is not that long. Okay, so we choose. So, of course, for the first digit, we cannot choose 0, yeah? The first digit cannot be 0, otherwise it's not an 18-digit number, yeah? Okay, so that means for the first one, okay, T0 cannot be, if T0 is less than 3, T0 it can still be chosen, yeah? We choose T0, yeah? Otherwise, what do we do? Okay, we choose T1, okay, and choose T2, choose T3, okay? Good. So basically pick a number. This one, okay, removes symmetry because 0 is special. All other digits are the same, yeah? How many ones, how many twos, yeah? Okay, all other digits are the same, yeah? Okay. So this is okay, actually a pretty simple program. That's it. Okay, let's run it. So start a Picat, CL P172. Good. And then let's what is the name? What is it? It's man or something? It's man. Okay, the top name is man. So man. Ooh, how much time? It's a. Oh, so it's 0 second. Right, so this BDD took BDD 7 hours to find this number, yeah. So if these two were paid by hours, then BDD would be as rich as Donald Trump, and this one would be still very poor, you know, because it didn't work for me so many hours. Okay. So next example. The next example is let's do queens. All right, so queens. So that's it, yeah? So queens, okay, so what do? We create an array, and okay, this model is, n variables, yeah? N variables, it's a board, yeah? So let's say the first queen is placed in the first column, the second queen is placed in the second column. Then we just need to determine the number of the row, yeah, for the queen, yeah? Okay, so the domain is from 1 to n, yeah? Okay? And then we use the loop, yeah? Okay, so it cannot be the same, not the same row, yeah? And also not the same diagonal, yeah? We use this, okay, to ensure they are not placed in the same diagonal. And then we solve, yeah? Solve, okay? So let's run it. Well, for this one, you can also run it as a standalone. Standalone, what the way to use it, you just say queens. Okay, this is 100 queen, yeah? So let's say we want to solve a bigger problem, yeah? So let's say Picat, queens. So let's say queens, let's say 1,000, yeah? And then see how much time it's taking, yeah? It won't take long because I did it before. Unless, oh yeah, it doesn't take much long, yeah? So 7 seconds. Okay, by the way, this is computer is not faster, yeah, it's i5, yeah? All right, we did something different. So you had a program to count the number of solutions. Yeah, let's change the program, okay, to do the same thing, yeah? So quiz. So what we do is here, solve, yeah? Actually, this is a built-in called count all. Okay, it takes a predicate and returns the number of solutions. Okay, so what do we do? So this time, we just say print. All right? Okay, maybe print ln, all right? Good. So then let's do it. Okay, queens. All right, let's say queens. What's the name again? What's the name? Okay, queens. 8. So 92, yeah? 92 is good, yeah? Let's say 14, whether something did 14. Well, it's slow because it only has one core working. Yeah, but still it's pretty good, yeah? All right. So this is, does it answer, does it answer questions? Yeah? All right, so let's consider another example. This is Sudoku, yeah? Sudoku. Okay, using set this time. Okay, actually this is, well, 9 by 9 is not interesting, yeah? It's like toy problems. Okay, we do 25 by 25, yeah? Okay, so this time we use set, yeah? This is a set solver. Okay, the set solver compiles everything down to a conjective normal form and then calls the set solver. Okay, in this system, it uses a link by armor, maybe Marcos knows him. Yeah, he is a professor in Austria. The author of Lingeling. Okay, so we so Sudoku set. Okay, so main. Okay, it starts solving. So you see it comes instantly. Yeah. So before it is message, it is compile time. It compiles down to conjunctive normal form. And then, okay, once you see this message, that means, oh, the set solver is working, yeah? All right, the last example is, there's a 15 puzzle, yeah? 15 puzzle. I showed you already, yeah? Okay, let me run it. Puzzle. All right, so I think that this instance called hard instance. It's hard because okay, it is one of the benchmarks used in the competition. Yeah, it's hard because it was hard for other solvers, but not for this planner. Yeah. Okay, so it is like that. Flops 15 puzzle. Okay, so this is the name of this is okay. It is called a test hard. Yeah, test hard. Okay, let me run it. Test. Let me take the time. Test hard. Well, you see, it's searching. Okay, it uses iterative deepening. Yeah. Okay, of course, it's beyond the power of Prolog. You cannot solve it using Prolog. It's too much. Yeah. You see, well, you see how many steps? It's 34 steps. Okay, you just take a look. Even if branching factor is 2, then to the power of 34, that's a lot. Yeah. For Prolog, because Prolog doesn't memorize anything. Yeah. Okay, this is good because it memorizes. Okay. Oh, I was there. So next time when I come there again, then okay, I know what I should do. Yeah. So that's why it makes this so effective. Yeah. Okay, you see, it takes less than 1 second. Okay, to solve the problem. All right, so that's the end of the demo. And also, 2 announcements. Okay, exciting news, ICOP will be in New York City this year in October. Okay, Andy is a co-program chair, and I'm a co-general chair. So it's a good opportunity to visit New York City, the capital of the world. And also, I'm looking for students. Yeah. Well, I have seen 2 people. Okay, looking for students. Okay, I don't mean to compete with them. So, but if you know any younger student who is interested in doing, actually there are a lot of exciting things here: planning, set compilation, and also applications. If you are know any bright young student who is interested in spending several years in New York City, yeah, let me know. All right. Again, thank you.
Look at that, we have a question at the back already.
The solver integration is very impressive, and
Thank you.
my question is, you can't use backtracking the predicates with the SAT node?
You can.
Oh, you can.
Yeah, you can. I can. Yes. Yes, can. Yes, we can.
Wow.
Yeah. So really, what you do is actually it's implemented this way. Okay, you use the solve, and then everything will be compiled to conjunctive normal form, and then thrown to the set solver. Once it's solved, then the system Picat retrieves the answer and then returns the binary. If you say, oh, this is not what I wanted, then you can backtrack. And backtrack, and then it compiles again, not compile from scratch. I mean, at least for example, if it's minimization or maximization, then it changes the bounds and then compile again, and then through it to it communicates with the set solver. Yeah. So this is a nice thing, okay, you can use backtrack with the set solver.
Can you tell a bit about the implementation? So what programming language did you use?
It's implemented in Picat.
Python?
I mean, the virtual machine. The virtual machine is implemented in C. All right.
Okay.
The compiler is implemented purely in Picat.
Yeah.
So Picat is still. I have heard several people doing projects using Picat, and still currently, Picat is still the largest application of Picat. It has. The compiler has more than 20,000 lines of code. Actually, it's pretty fast. It's pretty fast, and it takes, if you have a fast computer, it takes 1 second to compile everything. Yeah, the compiler, the library, it's pretty fast.
And how big is the virtual machine? Lines of code?
The virtual machine is, the source code is available. You take a look. Yeah, so you get an answer. Yeah, so it's about also 20, because the virtual machine has big arrays, just ignore those big arrays, it's about maybe 25,000 lines of code.
Yes, again?
So you've also mentioned that parsers are much more efficient because you can limit the backtracking.
Yeah. You mean for parsing?
Parsing,
For parsing, because in here we use, you can use pattern matching rules. Yeah. So okay, you parsing for a string, input a string. Okay, if this input string matches this pattern, okay, you derive it. Yeah, you derive it. Okay, since all the input arguments are indexed, unlike in Prolog implementations, only one argument and sometimes only the main function of the argument is indexed. That's really limit. Okay, this one is everything is limit. Everything is indexed. Yeah. Okay, so you will build a tree like okay. So I can use it to write a program and compare it with Prolog. You will see, oh, this program is 100 times faster. That's not surprising. Why? Because everything is indexed. I can write a program that is 10,000 times faster than Prolog. That's possible. Yeah. Why? Because what you need to do is you just throw in rules into your program. Yes.
Yes.
Do you have co-recursion in Picat?
Tail recursion?
Co-recursion, co-induction.
Oh, co-recursion, co-induction. No, because I don't understand it. You have to explain it to me. Yeah, I have heard of it. So, for example, Gopo Gupta is
Yeah, so
working on it.
this is co-recursion for Prolog, essentially.
Yeah. It sounds very interesting.
Yes. So actually, yeah, I just rerun the 14 queens. Yeah, actually, your number is correct. And the execute time was about 14 seconds. Yeah, yeah, only 3 orders of machine. So,
but it's not
without fast fail. So I think
but this comparison is well, you use multiple processes, and this
it's
one
a single
uses
core. It's a single core. Yeah.
oh, single core.
Yeah.
Well, then
yeah.
click is very good.
Yeah. Without fast fail. Yeah.
Yeah.
It's quick. We can compile it to see. Yeah.
Oh.
Yeah,
but still, that's very good because that's just backtracking. This one does propagation.
Okay.
Mm.
It's a my
But
question.
I have to say, when it uses propagation and when it searches all the solutions, okay, not that big difference.
So my question is that what can be the keys of attributes and maps? And can you use compound terms as keys of maps?
Yeah,
Okay.
yeah, you can use compounded terms,
Yeah.
but the only thing you cannot use is variables. You cannot say,
So
oh, I have a
they-
variable key.
So
No,
they must be ground terms.
no, not necessarily.
Not necessarily.
No, not necessarily. Okay,
Yeah.
keys can contain variables.
Okay.
Okay, as long as it's not a variable, then it's okay. Because a variable, using a variable as a key doesn't make sense.
So, but to me, the attribute and maps and tables are more or less similar. Yeah, they are all key and value stores. So
Hash
do you
tables.
use the
Hash tables, yes.
So do they use the same mechanism or are they implemented differently?
Well, of course, the function
Yeah.
that computes hash codes
That's good.
is shared by both. Yeah, and these tables are not map sets are not tabled.
Yeah.
No. Okay, so only tabled maps are tabled.
Yeah.
Tabled maps are tabled.
I see. Yeah.
Mm.
And my final question is, are tables first class or not? Yeah. So can I ask?
Are tables
as
first class? That's
Yeah,
a
yeah.
good question.
Yeah, yeah.
Because so for different applications,
Yeah,
you want
yeah,
to
yeah.
create different tables.
Yeah, yeah.
That's a very good
Yeah, yeah,
question.
Yeah.
Currently, no.
So I want to manipulate tables myself. Yeah.
Oh,
It
you
can be
want to
very useful.
manipulate
Yeah.
tables. Currently, no. Maybe we can start a joint project.
Any further questions? Oh,
One of the biggest achievement of Ueda-san's project, ICO project, is implementing operating system using logic program. Can you implement operating system?
I think so. I think so. Yeah, I actually heard the story. I did my PhD at the Kochi University, and one of the assistant professors spent time at ICOT, and he said, "Oh, this one. Oh, so I type something. It takes a while for it to come back. So, well, of course now it's faster. You can do it, but it doesn't make sense. It doesn't make sense to implement operating systems using this high-level language. Okay, you use a tool for something. Okay, the tool is suited. Yeah, you cannot use. I have this tool and I use it to do everything. And that's not a good idea. Yeah. Sure.
any final questions? Okay, if there's no more questions, we'll thank Neng-Fa again for a very gentle but also stimulating tutorial at the end of the day. Thank you very much.
Thank you very much.
And we will place the call for papers for IC LP out in the hall on the small table. So please take one if you're considering submitting, or even if you've got an office colleague who is considering submitting. Thank you very much.
Okay, so for the ticket for Super, I will stand by in maybe 15 minutes at the hotel. So, the market hotel.